3. This is continued discussion for section 3.1, vector valued functions. And so far we mentioned a vector value function in the two-dimensional space or three-dimensional space would represent a curve. And also, I believe in the last video, I showed how we get this curve. And also, we can take a quick look. I suppose this is a vector value function, right? And which really means x is 5 times cosine t, y is 5 times sine t, and using the famous Pythagorean theorem, Pythagorean identity, we get x squared plus y squared equals 25. So for this vector value function, indeed, it turns out to be a circle in the two-dimensional plane. And how about let's take a quick look at another one. Very similar, but anyway, this is a three-dimensional vector valued function. Okay, x equals 5 times cosine t, y equals 5 times sine t, and don't forget the z component, z is t. And if you only look at x and y, somewhat you can rush to the conclusion, you say, okay, that is the equation of circle again. But anyway, think very carefully. We're supposed to have a curve in the three-dimensional space. So what I said here is it's a helix spinning up around the z-axis, certainly with radius 5. And I guess it's not that clear what do I mean by a helix, how it spins up, those things. So I do have a graph. Hopefully it will show you the idea. Okay. Basically, what you can consider here is we are having, maybe just starting from the origin. Okay. Supposedly we may have a circle. And also I think it should be mentioned here at t equals 0. Yeah, this is not the point I should start. It should start from over here, I believe, at the x equals 1, y equals 0. And then we do expect a circle. But keep in mind the z coordinate, it is changing according to t. By the way, it's worth to mention t usually it is for time. So as time goes by, the z coordinate is moving up, right? So you can imagine you have a unit circle around the z-axis, and then each time it goes a little bit, and then point moves up a little bit, okay. And then eventually, as you can tell, the circle basically is transformed into a helix, and it is still centered around the z-axis. Certainly, if you consider circle, the projection of this entire curve into the xy plane still have a radius 5, a radius 1 here. That is a helix. And this is the introduction part of vector valued function. And more importantly, this is a calculus class. We want to consider the calculus for vector valued function. In calculus, we study limits, derivatives, and integrals. It turns out to be very simple for a vector value function. We can say the limit of a vector value function, it is still limit, and such that we only need to take care of the limit of each component. And similarly for the derivative of a vector value function, still it is a vector such that each component, it is the corresponding derivative. Very similarly, the untitled derivative, or really the integral of a vector value function, turns out to be a vector, and such that each component, it is the integral of the corresponding component. Or put it in a simple way, when you consider the limit of vector value function, basically there are 3 limits. And the same for derivatives and the integrals. Okay. How about let's take a quick look at what I have on this part of notes. This is a helix. Yeah, actually, I suppose limit might be easier. I guess we'll talk about some limit problem on the textbook. Okay. So this example, it is checkpoint 3.5. It is find a derivative. And so, as we just mentioned, basically we only need to find out derivative of the components. And for this particular part, the first component, I just want to mention, there is product rule involved. Product rule involved. Okay, U is T, V is log n of T. So using the product rule, we get the derivative first component as log n of T plus 1. Little surprising, right? Note that the derivative of logarithm of t is 1 over t. So if you look at second part, t times 1 over t cancel to 1. Okay. And derivative 5 times e to the t, it is 5 times e to t. Derivative cosine, that's negative sign. Derivative of cosine, that's derivative sine, that's a negative cosine here. That's a cosine. That's a cosine. Okay. Originally it has a minus. The minus still stays. Derivative of vector value function, it is a vector value function such that each component, it is a derivative of the corresponding component. Another one, find out the unit tangent vector to the vector value function. Remember we said a vector value function really represents a graph, a curve in the two-dimensional or three-dimensional space. So indeed, it is a curve, even though I'm not so very sure how the curve would look like. But anyway, it is a curve in the space. And also, it is a smooth curve. I hope you remember for any smooth curve, we always can have a tangent line. A tangent line touches the curve exactly at one point. So in order to find out the tangent line, you may want to consider the tangent vector. The tangent vector simply is generated by taking the derivative of the curve. So t squared minus 3 turns out to be 2t, 2t plus 1 turns out to be 2, t minus 2, it is 1. So this is the tangent vector. Certainly at a different value of t, there is a different tangent vector. The derivative still it is a vector value function. And also, in terms of unit tangent vector, I hope you remember in the discussion of the first week, for the unit tangent vector, it is vector of length 1, of magnitude 1. And in general, it's just easy. In order to find out a unit vector in this same direction, you only need to multiply by the reciprocal of the norm. So the next part, I just calculated the norm of the tangent vector. And certainly for different value t, there's different norm, different magnitude. And accordingly, the unit tangent vector always can be generated by multiplying this original vector by the reciprocal of its norm. So this is the unit tangent vector. And also you can give a try, maybe say plug in 1 for t, 2 for t, to see if the vector is a unit vector. It is a unit vector. Unit tangent vector. How about that? Let's take a break. Thank you for watching.